Today we'd like to take our study of batteries one step further. So in the last unit, we learned that batteries turn chemical energy into electrical energy. We saw the term voltage, which meant the energy per charge. That was the joules per coulomb that we were going to get from our battery. We saw the term current, which talked about the flow of electrons. It was the amount of charge that flowed through the wire per second. That was measured in coulombs per second, or amps. We saw that we could combine these two together and get power. So if we had a 9-volt battery and it was giving out a current of 2 amps, when we look at the actual units, we see 9 joules per coulomb. We see the coulombs cancel, and we're left with 18 watts, 18 joules per second. Okay, so we had the formula, power equals VI. So let's go a little bit farther. Your whole life you've been inundated with battery commercials with one company trying to convince you that their battery was better than another company. So you might have Duracell saying their batteries last 15 hours longer. You might have Panasonic telling you their batteries last 15 times longer. And you might have Energizer telling you that they have a powerful new look. Because let me tell you, the way the battery looks definitely tells you how powerful it is. Obviously, we want to actually figure this out using mathematics. We'd like to know which batteries are actually better. We don't want to fall for stupid advertising campaigns. So what you want to look for is battery ratings. Now there are 2 different ways that a battery company might rate its batteries. So this company gave what's called watt hours. Okay, so it tells us that this battery will last for 115.2 watt hours. What is a watt hour? It means you could get 115.2 watts for 1 hour before the battery will be dead. Obviously, this means the battery was fully charged. If you pulled this much power, it would last for 1 hour. This one measures it in amp hours. So this one is 2.6 amp hours. That means you could get 2.6 amps for 1 hour, and then the battery would be fully drained. Okay, so these don't seem so useful, so let's see how we have to work with them. Let's start with the 115.2 watt hours. Remember that a watt is a joule per second. An hour is 3,600 seconds. So you take watts and replace it with joules per second. You turn hours into seconds. The seconds will cancel, and when you multiply those out, you will get 414,720 joules. I don't know why the battery company just can't tell you how many joules are on the battery, but this is what you have to do to get that. With this company, it's 2.6 amps. Remember, amps are coulombs per second, and it will last for 1 hour. So we multiply those two together, and we get 9,360 coulombs. It still seems like we can't compare batteries. This company is telling us how many joules are on the battery, and this company is telling us how many coulombs are found on the battery. So we got to go another step. We start with the joules, and we realize if it's 19.2 volts, that means 19.2 joules for 1 coulomb on that battery. So we put the 19.2 joules on the bottom, the 1 coulomb up top, and we get 21,600 coulombs. For this company, we start with the coulombs, It's an 18-volt battery. That means 18 joules per coulomb. The coulombs cancel, and we get 168,480 joules. We now can compare energy to energy, or coulombs to coulombs. It's a lot of hoops to jump through, but you can intelligently figure out what a battery is going to deliver for you. This might be important if you're trying to buy a battery for a certain task. So let's say you're buying a battery to recharge your cell phone. You know you're going to be away from an outlet for a long time. Maybe you're going camping for a week, and you want to buy an external battery pack. So when you look at the external battery pack, it will give you a unit, in this case 25,800 milliamp hours. They're trying to make it seem like it's a very powerful battery. Realize that you got to get rid of the milli. They're just doing that to trick you. That really means 25.8 amp hours. That means 25.8 amps for 1 hour. When you multiply that out, you get 92,880 coulombs. That's how much energy, that's how much charge can be stored on that battery pack. Since this is a cell phone battery, we're going to assume it's 3.7 volts. That means 3.7 joules for 1 coulomb. And that means that this battery pack actually has 343,656 joules of energy. That's pretty impressive. That's almost the same amount of energy we had on this power pack for our power tools. It's more energy than was on this power pack battery. So we get lots and lots of energy on the battery, and that's, after all, what you want to buy it for. We don't want to buy it because it looks cool. We want to buy it because it actually will have a lot of energy stored on it. Let's see what we can do with this. So let's say we were going to buy a portable coffee maker. So it's powered by a battery. I hope you can see here, but if not, I'll tell it to you. The battery is 10.8 volts, and when fully charged, it's got a rating of 4 amp hours. So let's see what we can do with this battery. Start with the 4 amp hours. That means 4 coulombs per second for 1 hour. That is going to give us 14,400 coulombs. When that battery is fully charged, and I hope it's fully charged when you bring it to the work site, that's how many coulombs are found on it. It's got 10.8 volts. That means 10.8 joules per coulomb. The best you could hope for from this battery is 155,520 joules. Well, is that good? Is that bad? Let's actually try and do something with this battery. Let's use it to heat up water. That's the whole purpose of this thing. So we're going to heat the water from room temperature up to 100 Celsius. And I would like to see how many cups of water I can actually heat up. Am I going to be able to make 5 of these, 10 of these, 20? Let's see. So we put the energy that the battery has. We use the specific heat of water. We use the change in temperature, and we're going to have to raise the temperature of the water almost 80 degrees. And we solve it for mass. So if you take a moment to do that, you will get a mass of water of less than half a kilogram. And since it's water, we can turn this into milliliters, and we see that this thing is not even going to heat up one small water bottle worth of water. The small water bottles that you might get are usually about 500 milliliters. This guy could not even make 500 milliliters worth of coffee before the battery was drained. So this might not be your best option if you're trying to heat up more than just a little bit of water. Here's another crazy one. This is from the 1950s. The Everready company had an interesting way of describing how much energy was in their battery. They claimed that they could lift a 110-pound circus performer up to a height of 99 feet with the energy from one of their batteries. That seems a little odd that this could lift the circus performer up to that height. So let's try it. So the energy that we're giving this circus performer is gravitational energy, 99 feet. We want to turn that into meters. 9.8 is our planet's gravitational field, and it's a mass of 110 pounds. Convert that into kilograms, put that in here, put your 99 feet into meters and put it in there. See how much energy we're going to need to lift them to that height. Okay, and then we'll see whether or not this battery has enough energy to do that. Okay, I don't know the battery back from the 1950s, what it was like, but I can look up the modern day equivalent. It is the Everready Super Heavy Duty, which is the same type of battery that they were using back then. And if we look online, it tells us that it is 800 milliamp hours. We know that it is 1.5 volts. Okay, so let's figure out how much energy is in it. 8 amp hours that'll guess how many coulombs are on it. Then we have our voltage, so we convert the coulombs into joules. And when you get an answer, compare it to the answer we got from the previous slide. Does this have enough energy to lift that person to that height? And if so, could it have actually lifted them higher? Could it have lifted a heavier person to that height? So figure out for me, what is the heaviest person I could have lifted to that height? Or if we can't lift the person to that height, how high could we have lifted that circus performer using the energy in that battery? All right, hope this gives you a better feel for how we figure out what is actually stored in the battery and what we can do with it.